Hello everyone and welcome to our show. Today we're going to take a deep dive into the mysterious world of quantum phenomena to uncover some of the mysteries behind supergiant stars, fiber cable and rainbows. And maybe we will even learn a little something along the way. But first, let's take a second to check in. Are you ready? Are you excited? If you have been having a bad day, here is a picture of a cute puppy. Feeling better now? Okay, let's begin. A little bit about us. We are a team of 4 undergraduate physics students at UCL. I'm Anastasia, that's Clive, that's Gregory, and this is Joe. Our mission is simple. We want to deliver physics in a way that makes every second of studying interesting and enjoyable. Today's topic is macroscopic quantum phenomena. I know that it sounds kind of complicated to you right now, but I promise you that by the end of this video, you'll feel so confident in your knowledge that you're going to be the one running this segment next time. So, before we get into anything too crazy, let's first take a step back and talk about how quantum and classical systems are different. Macroscopic systems are deterministic, which means that they can be predicted through initial boundary conditions. That is why they're called classical systems. Microscopic systems, on the other hand, are non-deterministic, meaning they cannot be predicted due to uncertainties in boundary conditions, and these are quantum systems. You can already see that macroscopic events can be explained through ideas of quantum theory. Interesting, isn't it?
So before we go any further, I would like to explain the root of quantum physics. The best way, in my opinion, to think about it is to think about light. So what is light made up of? Light is made up of photons in physics. And so what are photons? Photons are packets of energy. So when people go around to asking, well, what is the nature of light? Physicists were very intrigued to discover that light carries both wave characteristics and particle characteristics. So with no other way to answer the nature of light, physicists around the world hence agreed to a new concept, which is the wave-particle duality concept, which hence becomes the root of quantum physics.
The boundary between quantum physics and classical physics is debatable, as macroscopic bodies do experience quantum effects but are actually too small to be relevant. For example, a human sitting still would have an uncertainty in position less than the size of a proton, and an uncertainty in velocity roughly 1 proton radius per month. These distances are far too small even for the world's most accurate measuring devices, so relatively large bodies can be safely limited to the classical equations of physics. Although quantum effects are too small to have any significant impact on macroscopic objects, some astronomical events can only be explained from a bottom-up quantum approach. A neutron star, for example, is a collapsed core of a supergiant star, and they are some of the smallest and most dense objects in the universe. They can have the radius on the order of the distance between Wembley and Watford, but the mass of more than 1.5 suns. These bodies mainly consist of neutrons, hence the name, and this comes about due to the electrons and protons coming together forming neutrons under the conditions present. So what force acts against the pull of gravity to sustain such an object from collapsing inwards towards itself? The answer is neutron degeneracy pressure. This effect comes about due to the Pauli exclusion principle, which disallows any two fermions from occupying the same quantum state. As the neutrons come closer and closer together, their position becomes more defined, thus increasing the uncertainty in momentum due to Heisenberg's uncertainty principle, inducing large kinetic energies which push against the inward gravitational force. This effect is also responsible for the formation of other astronomical bodies, such as white dwarfs, where instead of neutron degeneracy pressure, electron degeneracy pressure is present. Both of these are type of quantum degeneracy.
From data communication to glasses, microscopic properties of light can be seen everywhere. The superposition principle can be used to explain the slowing down and changing direction of light through transparent mediums. Viewing light as a wave, as photons enter transparent mediums, electrons vibrate, forming additional waves. These superpose with the light, causing the light to slow down. In the words of Feynman, the bending of light rays comes about just because the effective speed of the waves is different in different materials. Using the shortest distance principle from last year, this phenomenon now becomes apparent even from a microscopic perspective. Unfortunately, there is no pot of gold or leprechaun at the end of the rainbow. The mystifying nature of rainbows can now be demystified through refraction, reflection, dispersion of light through raindrops.
So today we learned about classical quantum systems, quantum theory, and the macroscopic quantum phenomena. What topic do you think we should cover next? Let us know in the comments, and if you haven't already, smash the like button. If we reach 300 likes, in the next video we'll explain Fermat's final theorem. In the meantime, keep loving physics and we'll see you soon.